to Consistently Eventful, talk about event sourcing in Kotlin. So I'm just going to start off with a quick introduction. My name is Trafton. I'm a principal software engineer at Adobe Mutual. Work out of the Dover, New Hampshire office, but a frequent visitor to Boston. Not a huge Twitter user, so if you do need to connect with me, believe it or not, email is actually the best way. And you'll find these slides afterwards. Fun fact about me, I'm a huge pizza aficionado. Just wanted to share this. This is a pizza I made in my oven the other night. Homemade dough. Very proud of it. So I thought I'd share it with you all. So speaking of pizza, what's on the menu for our talk today? We're going to start off with an appetizer, which is an event sourcing overview. So I'm going to go a little bit into the event sourcing concepts and the terms involved. In general, not specific to Kotlin. I'm going to show a demo, which is written in Kotlin to demonstrate some of the features of event sourcing. For our main course, we'll talk about really what makes Kotlin a great fit for event sourcing and why we use both at Liberty very frequently. And then for dessert, we'll just talk about some of the strengths, weaknesses, and strategies of event sourcing in Agile. So let's talk about event sourcing. I'm going to throw some buzzwords on the screen. Have you guys heard any of these before? Is anyone familiar with event sourcing and some of these words? Yeah, so people throw these around. They all sort of mean slightly different things, but they're often used in the same sentence. So we're going to try to differentiate a bit. Let's start out with event sourcing itself. So event sourcing, what it really means is your system of record is an immutable event store. It's a series of events captured from your application, stored chronologically. That's your system of record. These events are published to the system, yeah, it can be handled by event handlers. Handlers usually generate a projection, which constitutes your read model. So for example, if you need to retrieve details about some business entity, you would read those from your read model. And then projections can be torn down and rebuilt completely based on the events. So the events are truly the source of truth about your data. Projections are just a temporary, almost cache, you can think of them as. And as such, you can tear them down and rebuild them completely from scratch based off of your event stream. In the diagram you see here, we're going to go over this in a little bit more detail, but you can see, for example, from the presentation layer, in this case, this is like a shopping application. And so you have like the cart created event, item 1 added, item 2 added, item 1 removed, and then shipping information added. All of those are persistent. And then they're stored in the event store and then published to generate that materialized view, which sort of looks like a relational database diagram. That's often what's used. And then you can also flush those events down to other external systems for reporting, for side effects, for other downstream entities that might be interested in those events. So we talked about event sourcing. Let's talk about this mouthful, Command Query Responsibility Segregation, or CQRS. So this one is actually quite a bit simpler. Basically what it means is you're separating your write model from your read model. It doesn't necessarily have to leverage event sourcing, although it often does. And when you build these systems, you set them up such that your commands are task-based rather than data-based. So in the example you can see here, an example of a command might be book a hotel room, instead of take that reservation status field and flip it to reserved. And then eventing, like I said, is typically used to synchronize between the write models and the read models. So after you ingest a command, you validate that that command is appropriate at that time given the current state of your application. You can flush that down to the read model via an event. And then domain-driven design. So this is really a technique used for designing and building your applications that allows conversations between the business team and the technology team to flow a little bit more smoothly. So the idea here is that you work with business teams to identify the commands and the events that are relevant to your system in sort of plain English that anyone off the street can understand. Like we were talking about with CQRS, it's much easier to talk to a business team about what booking a hotel room means rather than what updating a certain field in your database to a certain enum that they may not have awareness of. So it creates what's often called like ubiquitous language or design language for your application. And this allows conversations between the business team, the technology team to flow a little bit more smoothly. And it also means that your domain or terminology from the business world is sort of encoded in your technology as well, in your code base. And that can make things a lot easier for maintainability and reliability down the road. So just a couple of glossary definitions. We touched on commands, some details about commands. They're typically written in the present tense, and they indicate an intent to mutate the state of your application. So in this case, a good example is like change policy address. That's one that we use a lot at Liberty. Aggregates. So aggregates can be challenging to understand, but the easiest way to think of them as state machines. If you guys have ever used like Redux or really any other event-based state-based pattern, essentially they ingest the command, they receive the command, they decide what to do based off of the state of the application and the data that's provided in the command, and then they issue events, which indicate that like, yes, this thing definitively happened. So, for example, that change policy address command, we might take in that command, which represents an intent to mutate the state of our application. We might verify that that's a real address, right? We could use a Google Maps API or whatever to verify that, yes, this is in fact a valid address. And then the aggregate would then issue an address changed command, or sorry, an address changed event, which says that like, yes, this address changed in our system. It happened. And that goes to that immutable append-only event store. So yeah, like I mentioned, events are typically the result of commands, and they're always written in the past tense. Like I said, I can't emphasize this enough. Events are something that happen in your system. You can never take them away. So I touched on the event store. This is usually, there's several event stores available out there. You can write your own. You can just use a SQL database. It doesn't have to be complicated. But the key is that it's the append-only immutable store of all of your event records. We talked about projections. So the key with projections, it represents the current state of your application. They can be torn down. They can be rolled back. You could actually generate projections at certain points in time if you wanted to for reporting. And then a bonus thing that we're not going to dive into too much today, but I actually love this pattern. We use it a lot at Liberty, which is called a saga. And sagas are usually used to model complex business processes where you have a lot of data flowing in and out. So say, for example, you receive an order and you have to coordinate with 7 other systems to process that order. You would have an order saga which maintains the state of that business process, what step it's on, what it needs to retrieve, what it's waiting on. And it's just receiving events from those external systems and then issuing commands based on those events. So say step 1 completes, it might say, okay, I got the event that says step 1 completed. Now I'm going to fire off a command to request that step 2 begins. You can fire off commands in parallel. So you receive the event from step 1 and you want to execute steps 2A, 2B, 2C at the same time. You can fire off those commands in parallel and then receive them in parallel. So it can really help accelerate your processes in that way. These tend to be a little more complicated. We're not going to really demo that today, but for more complex applications, this is certainly a pattern that's very helpful. Okay, so this kind of summarizes that whole view. We have our application interface that could be an API, it could be CLI, it could be just about any way you interact with your application. It takes in commands. Those commands are processed by the aggregate. That's where business validation occurs. So the aggregate determines, based on the state of the application, if that command is valid. If it is valid, it can issue 1 or more events based off of that command. Those events are written to the event store, and once they're in the event store, again, they happened. There's no going back. Those events are typically broadcast to event handlers, which generate a projection. And the fun thing about projections is that your projections can be just about anything. So we actually have a use case that we're working on now at Liberty where we have our event handlers generate a regular relational database for quick lookups, joins, that sort of thing. But those same events are used to generate a Elasticsearch instance, so we can do complex like fuzzy searching. And those are automatically kept in sync because they're based off of the same source of truth, which is our event string. I also like this because it has a really nice symmetry to it, and you can kind of see where command query segregation comes from. So we have our commands on one side, our query side is on the other side, and then they're all sort of kept in sync via that event store. I'm also personally a huge fan of one-way data flows. I've been working with Graph for quite a few years, and I really enjoy how this kind of has a circular aspect to it. So information comes in one end and comes out the other end. I find that it makes it very easy to reason about and debug. Okay, so let's dive into our first course, which is a demo. Let's talk about our problem space. So we all, collectively are the CTO of a brand new company, 10-Second Pizza. So it's delivery pizza with a twist. Not to be outdone by Uber Eats, the business is guaranteed delivery in 10 seconds or less. So we're responsible for building the online interface to take in orders. And we talked to the business team and we asked them, so for reporting, like what kind of information do you need? Like, what kind of reports do you want? And they said, just get everything, grab everything, which I'm sure you've all had this conversation before. Okay, so this is our problem space. Let's see if we can condense that into some technical requirements. So if we're going to be processing these orders quickly, our system needs to be fast. The business has promised 1 million users by the end of the year, so we've got to be scalable. We're going to provide an API for use by front-end and mobile apps. And then we're going to, quote, capture all of the data for reporting when the business decides what they want to report on. So these are all good use cases for event sourcing, and we'll dive into that. But first, we're going to do some event storming. So this is going to be like an event storming light. Usually be quite a bit more involved, and we can spend a whole talk just talking about event storming techniques. So we're going to do the quick and easy version, the fun and easy version, based on the title of my talk. So we had a conversation with the business team, and they said, okay, these are the things that a customer can do. They can start a new order, they can select the size of the pizza they want, they can select some toppings, and then they can go ahead and submit the order. So these are all things the customer can do. So we were talking to them, and we said, okay, so the events that come out of that are an order was started, they selected a pizza size, they added a topping, removed a topping, and then they went ahead and submitted the order. So you can kind of see probably already how these are going to map to our commands and our events. We have our intents written in the present tense on the left-hand side, and then the resulting events written in the past tense on the right-hand side. Okay, let's dive in. Just have to find my ID. There it is. I'll probably bump up this text. Huh? It's probably a little small. Is that big enough to read back there? Bigger, or is that good? A little bigger. All right. All right, cool. This doesn't fit a whole lot on the screen. All right, so it's probably hard to see the repository structure over here, but I wanted to just kind of start to show why Kotlin is such a great fit for event sourcing. So let's have a look at some of our commands. So first of all, oh, that just got small again. That's going to be annoying. All right, I'll just continue. So our order command is just an interface. It has an order ID. That's all we need. That's the basis of our order command. And then we have several additional commands based off of those intents which we discussed. Commands are typically modeled as data classes. So they're very convenient to use, they're immutable, they have inheritance, all of the fun things we love about data classes. And so you can see they're just really, really simple models of an intent to mutate the system. So in this case, this command is select pizza size. And we have an order ID and the size that the customer selected. We have select pizza toppings, which is just very similar. It is a data class which has an order ID and then the list of toppings that the customer has selected. For starting a new order, we have the order ID and the username of the user who submitted that order, or who started that order. On the event side, again with the symmetry, these are pretty much one-to-one. The one difference you might notice is that we model our pizza toppings as added and removed events. This is really useful because, let's say, and this is a bit of a trivial example, but the business down the road might ask, well, what toppings do people consider and then get rid of? In a traditional CRUD-based model, you wouldn't have any record of that unless you purposefully added auditing for that specific question that might be asked. Chances are you're not doing that unless you know that that's a question that you're going to have to answer ahead of time, which is rare. So we model them in that way to really try to break down interactions with the application into as discrete chunks as we can. So that's why we model it that way. And we can look at a few of those. So selected pizza size, same deal. You probably get the pattern by now. Let's look at something that's a bit more complicated. We'll have a look at the aggregate. Okay, so I said aggregates were essentially state machines. And let's just have a look at this top level here. So the aggregate tracks the information that it needs to make business decisions. So in this case, we might need to know what the pizza size is, the pizza toppings, the submitted date, and the status. In this case, it lines up pretty well with what our sort of business entity model for an order looks like. But oftentimes, it doesn't. So you might track additional information here that you don't track in your entity, or you might track less because you don't care about it, you don't need it. For example, if you didn't care about what size it has, there's no need to track it here. So I'm not going to go too much into the plumbing of how this is set up. This is a pure Kotlin implementation of an event sourcing framework, light. There are other frameworks which we'll talk about a bit later. Like I said, I don't have a ton of time, so I don't want to get into plumbing. But let's just look at some of the cool language features that Kotlin allows us to do. So event sourcing is a very asynchronous event-driven pattern, or message-based pattern, I guess is probably more accurate to say. So commands and events are both a form of messages. And when we have our handlers, the kind of routing and handling is super easy in Kotlin because we have language syntax features like the when, the is, check. So when we get a command in, we just receive the interface, and then we can decide what to do with it based off of which subclass it is. And then inside each of those handlers, I came from a functional programming world, and function overloading is one of my favorite things in the entire world. So I love that Kotlin has it, and it makes it really nice to write these handler functions because you can just handle each command in turn. So we have handlers for selecting the pizza size, selecting toppings, submitting the order. Here you can see a bit of business logic. So when we handle the submit order, if the status is not incomplete, which is to say it's completed or in process or whatever, we throw an exception because we say, whoa, we can't process, we can't submit an order that's already been submitted. And you can imagine whatever business validation logic you might want to include here. A key part of these command handlers is this last line here, publish. So let's take a look at the select pizza toppings command handler. So over here we get the list of toppings, we do some diffing to understand which toppings were removed and which toppings were added. We generate events based off of that discovery, and then we publish those events to an event stream. And then our downstream handlers can handle them however they want. And again, those downstream handlers can be anything. It doesn't even necessarily have to be any sort of persistence layer. So let's say you had a feature where if someone adds pineapple to the pizza, you want to send them a text message that says, whoa, 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 what are you doing? Pineapple's a garbage topping for pizza. My personal opinion. Controversial, I know. So you could do that with event handlers, right? You could accept that event and say, oh my gosh, this user added this topping to their pizza. We we better let them know that they're seriously misinformed. So that's really the goal of aggregates, is they take in the commands, perform business logic, process the data, and publish events to the event stream. They also typically update their own state in the process. So you can see here we're actually updating the state and modifying the to a set. Okay, so let's just talk about one more architectural piece. Oh, sorry, question? Yeah?
Just because we're on the aggregates, how do you scale an aggregate?
Yes. You're talking about like rebuilding state based off the event stream?
Yeah, rebuilding or just scaling it.
Yeah, that's a great question. And it's actually, I was going to talk about my weaknesses slide, but we can talk about it now. So, oh yeah, I'm sorry. The question was about how do you scale aggregates? One of the critiques of event sourcing is you'll notice that this aggregate represents a single order. So if your system is handling 10,000 orders at a time, you've got 10,000 instances of this class living on your system at a time. That's a real problem. It really is. And it may not be appropriate for certain use cases because of that. Because obviously that uses a lot of memory. And we all know how much we love out-of-memory exceptions. The other critique of aggregates is so let's say you have an aggregate, right, that represents an order, and you deploy a new instance of your application. Well, that aggregate was stored in memory in the application. So when that new instance starts up, it does not have that aggregate. So typically what happens is the first time you try to issue a command to that aggregate, the framework or the system will rehydrate the state of the aggregate based off of the previous events that aggregate has processed. That can be a problem if you have 1,000 events for an aggregate. Let's say you just want to modify one small piece of state. If it has to replay all of those events in order to just modify that original piece of state, that can be a real problem. There are workarounds. So what's often employed is what's called a snapshot. So what the system will do is every end events or every day, however you want to calibrate the system, it'll generate a snapshot of the aggregate state. And that way, when it's rehydrating, it has a snapshot as a base, and it can just replay the events since the previous snapshot. A great question. And sorry for not repeating. So I was going to talk about one small sort of like architecture piece with this. Typically, when we're building these, event sourcing tends to add some level of complexity to your project. You don't necessarily want callers or clients to your application to have to think about that complexity. So typically what we do is we abstract all of that from any downstream callers in a service. So you can see here, usually it's pretty straightforward, right? So we have a service, basic stuff, we can list orders, get order, we can create an order, this generates the start order command. Where it gets kind of fun is updating. So we typically do something like this. You don't have to, but if you want to build a sort of REST compliant API, how do you translate an update into a series of commands, right? You might be updating several fields at once. You might not be updating any. So this is usually something we do to kind of build the glue that bridges that together. So we actually do some diffing here, where we check to see if like in this example, we check to see if the size is equal to the previous size, and then if it's not, then we issue that command. And same thing with the topics. So this is kind of a convenience wrapper. If your API is very task-based, where you're just saying, okay, customer updated their address, customer updated their pizza toppings, you don't necessarily have to do this. This is just sort of a convenience way to build some glue between our REST API. What's nice about this, I'm not going to spend too much time in the web layer of this application. If you guys saw the previous talk by my coworker Mike, he mentioned HTTP 4K. We do use that quite a bit. That's what this uses as well. But you'll see these handlers are roughly akin to controllers in sort of MVC web applications. And you can see there's no concept of event sourcing here. So all they know is that they just call the update order service, and off we go. Okay, so that's all well and good. That was a lot of code. Let's see if it works. So just start up a web server. First thing we're going to do is create an order. I don't know if I can increase the size here. I apologize. I will narrate. So this is Postman. It's a tool we use a lot for testing APIs. For those of you who are more Android-based, even if you are, you possibly have used Postman before to understand how APIs work. But I'm just going to use this to show how this application works. So the first request I'm going to do is going to create an order. So just create an order. We created with this UUID here. And I'll go ahead and actually I can retrieve the order. So this pulls it back. We haven't done anything yet. Let's update the order. So drop that in here. We'll set our size to small. Now let's go large. Okay, that updated. One thing you'll notice here that I want to call out is you'll notice this API isn't returning the updated order. It's just returning the order ID. We'll get into that a little bit later. Keep that in the back of your minds. Okay, so our application works. That's great. What I've done for this demo today, we never do this in production, but we're actually using files as our persistent storage. So you probably can't read this over here, but I've got an events.json file and an orders.json file. So if you look in here, you can actually see these are the two events that we created. So we've got our first event, which is the start of new order event. It contains the order ID and the username of the person who submitted it. And then we've got our second event, which was selected pizza size. There's the order ID, there's our size large. So once again, this is our system of record. This should never get changed, it'll only be added to. Over here we have what's called our projection, like I talked about. So this is roughly akin, it's just a key value store, the order ID and the order itself. This could be like a relational database. This is like cache state of our application. So one cool thing about event sourcing is because the projection is not our system of record, our events are. Let's say something needs to change with our projection. We can easily replay events and rehydrate that projection based off the historical events. So, like in our case, let's say everything's going great, customers love it, business team comes and says, okay, I want to know how many orders each customer has submitted. And you go, something's missing from our projection. Anyone see anything to identify a user there? Yeah, so that would be a problem. However, in our events, we're capturing the username, so we know we've got that data. We just need to rehydrate the projection to generate that. So what I'm going to do here is try to set up on a separate branch. I'm going to call it a replay. And so our orders.json, no username. What I've done is I've added in this branch username to our entity model, our projection model. So what I can do is just completely wipe this away. Again, this is disposable. Don't care about it. I'll start our application up again. And I've set up this special route, which will rebuild the orders. So go ahead and hit that. Okay, we got an OK response. Let's check out our projections again. Oh my gosh, there it is. We've got our username. We can run that report. Business is happy. We're happy. We didn't lose any data. So that's one of the big wins of event sourcing. It's great for if you're practicing Agile development, because as you know, Agile is all about moving quickly, shifting, pivoting. With event sourcing, you have your events. They happened. They're locked in. If you want to model your data in a different way, for your reprojections, if your use case changes, very easy to do. You just rebuild your projections. We even do some cool kind of blue-green style projection rebuilds at Liberty. So we'll have our existing projection, and then we just rebuild a new projection next to it, because if we have hundreds of thousands of events, it can take quite a while. Once that's configured and ready, we migrate and use the new projection. Pretty cool stuff. I think I have time for one more piece of the demo, which I didn't want to show. So I'm just gonna, let's give ourselves a clean slate here. Wipe that away. I'm gonna check out another branch. So we talked about separating your reads and your writes, right? And typically writes are the more expensive operation. And I've just gone ahead in our order repository, in the save command, I've added this thread.sleep for 5,000 milliseconds, kind of modeling a long write. If the database is locked or whatever, that obviously constitutes a problem. So let's say I go to create an order now. Well, I better start the order first. And we'll wait. And wait. And wait. Okay, finally finished. 5.87 seconds. So obviously for a company that's supposed to be delivering pizza in 10 seconds, spending 5 seconds waiting for an API request to complete is really not going to work. And what's happening here is when the customer submits that intent to start a new order, we are receiving a command, processing the command, issuing the event, and then running all the event handlers synchronously before this response returns to the client. But we don't necessarily have to do that, right? So if our customer, they don't care that they started an order or not, like the system is created, all we need to get back to the client is the order ID, which we can do because we generate that ourselves. So what often happens in highly scalable event-sourced systems is you have asynchronous event processing. And oftentimes it's actually split out into two completely separate services. So you could have, let's say you have a Docker container which is running your API, it's always up, it's highly responsive, and then you broadcast those events using Kafka or RabbitMQ or Amazon SNS, whatever you want to use. And you can have lambdas on the back end that are listening to those and processing those and generating the read logs. So just to kind of simulate this, I'm going to go over to our event store. And I'm going to use, I know you're not supposed to use global scope, but just for simplicity, I threw it in there. So this is wrapping the event processing in a coroutine. And this will allow us to process those events asynchronously. So let's start this up again and see what happens when we go to submit an order. Okay, well started, so 5.87 seconds, remember that. Okay, that was 800 milliseconds. So we dramatically improved the response time just by processing those events asynchronously. So that's kind of a brief overview of some of the things that make event sourcing great. So let's scoot back to my presentation here, and we can review why so many Kotlin language features work so well with this type of system. How are we doing on time? Good. Okay. So our main course, Kotlin and event sourcing element. So I did talk about this, and I kind of touched on all these, but I just wanted to make sure I'm leaving them. So data classes, first and foremost, their immutability, serialization for like writing to an event store, using inheritance and using that inheritance to define like event types is super useful, and then obviously the predictability of that immutability. I like to say Kotlin has superpowered syntax. It's just expressive and powerful control flow statements, so using when, using function overloading, and then for event-based systems, strong typing actually is a huge plus because it gives you predictability about what's going to be contained on an event and what isn't. And also null safety, something we all love. Also coroutines. So in the case where your system is not actually separated into multiple systems for writes and reads, if you want to do any kind of asynchronous processing, you can use coroutines. they're also great because we actually have some use cases where our event handlers at times process events synchronously and at times process them asynchronously. So for example, if we have a very read-heavy application where we really want our projections to always be as up-to-date as possible, we can process those events synchronously. But let's say we have some downstream notifiers that just at some point want to know that this happened. We process those events asynchronously, and they're more fire and forget. And that way we don't have to wait for them to complete before we return the response to the caller. And another thing I think doesn't get talked about all that much with Kotlin, but because it runs in the JVM, you get all of the benefits of using Java, plus all of the amazing things about Kotlin. So the rich ecosystem of utilities and frameworks, so we use Spring quite a bit at Liberty. We also use several other Java libraries that are very helpful to us. Being able to run it basically anywhere, that's the promise of Java, but particularly for us, we use a lot of AWS Lambdas, and being able to run on the Java runtime in AWS is huge. Obviously, the JVM is highly optimized for performance, and it's an incredibly reliable system, which is part of the promise of event sourcing. Okay, dessert. Strengths, weaknesses, and strategies. So I'm going to start out with weaknesses. Event sourcing is not the solution for everything. It's great. We use it a lot at Liberty because it really fits our business model. But if you're just running a basic CRUD application, it's a really bad choice. As you saw in the code that I demonstrated, there's quite a bit of boilerplate. There's quite a bit you have to do just to select a pizza topping size. And if that's too much overhead for you, that's fine. It doesn't work for everything. Eventual consistency can be a problem. So this is the lag time between when you receive the command and when it gets written into the projection. So if you are processing those events asynchronously, it can be a problem. If your read model is out of date, customers can get really confused. In our case, if a customer submits a claim or applies for a policy, and then they reload the page, and all of a sudden that claim is gone, that's a problem. That's a big problem. So eventual consistency is something to definitely keep your eyes out for. And then we already talked about this, the high memory usage. So in systems with a lot of concurrent aggregates, you can run into memory problems. And something you just kind of have to manage. Strengths. So for us, I like to say it has flexibility through replayability, which is not a word according to PowerPoint spell check. But I put it in bold, so it really makes it feel like a word. So this is what kind of showed before. So our projections can be anything we want them to be. We can rebuild and rebuild them however we like, based off of the current needs of our application. So that provides a lot of flexibility. Where reads and writes must scale independently. So in the case where you have an extremely write-heavy application with very few reads, you can create systems where your writes are horizontally scalable, and then your reads can be scaled at a lower rate. So you might have 7 instances of your write processor handle running, only 1 of your event handlers, because that can be slower, not as much traffic, etc. It also works really well in an event-driven microservice architecture. So again, at Liberty, we use Lambdas quite a bit. We use event-based architectures quite a bit. And this works really well because one of the great things I like about it is you can take in events from other systems, and those can just become events in your system. And they can be handled just like events from your system. That makes processing them really easy. And it also makes replayability really easy because you don't have to go out and make that API request again. You already have the data from the previous call to the microservice. And the examples you'll always see for event sourcing is anything that's transaction-based. So the go-to example is like a shopping cart, a bank, ordering a pizza, not as transaction-based, but and anywhere where history matters. So where you care about what happened, event sourcing is great. And that's something that a traditional CRUD application can't really provide, because all you have is the current state. You don't know how you got there. And another thing, I didn't touch on this too much, but the testability is great, especially for aggregates, because they are state machines. So it's really easy to say, okay, I've got my aggregate. Given that the aggregate has received these commands, when I send it this command, I expect this to happen. So it's really easy to test because they're just pure functions almost. They have a state, you send them a new request to change something, and they tell you, yes, I can change this, no, I cannot. Okay, and just I want to leave you a couple of strategies if you decide event sourcing is right for you and your APIs. So first big thing is eventual consistency. That's the thing that gets you every time if you're not prepared for it. So you definitely want to have in-depth conversations to make sure that it's either acceptable or you have a plan to mitigate it. Working with business teams to define domain language. That's that DDD, domain-driven design, that we talked about earlier. That's key, because if you can encode that domain language in your application, it makes it really easy to talk about with your product owners, with your business team, as well as your fellow developers. I would highly recommend using a framework. So for the code examples that I showed you, I just kind of spun up my own rudimentary event sourcing framework in pure Kotlin, because I wanted to show that. But there's a lot of production-ready frameworks out there we could use. One of them that I really like is Excellent framework. It's written in Java, but it has nice bindings for Kotlin. I talked about abstracting your event sourcing paradigms with services, so your downstream callers don't have to worry about them. And if you look at event sourcing on the internet, you'll see a million stories about people saying it's a bad idea, don't do it. The key is don't force it. So right tool for the right job. In our case, at Liberty, it is the right tool. It may not be for yours, but certainly something to consider with any architectural pattern. Okay, thank you. That's it. Thanks for sticking it out for the late presentation. I guess we've got a couple of minutes. Does anyone have any questions? Oh, is there a mic? Okay, we've got a mic. We're good.
When you're rebuilding your models and tests, do you rebuild from projections and apply events to that projection, or do you rebuild events all the way down?
So the events never get rebuilt. So the events are your immutable data store.
Yeah, but like in this environment, right, you have your aggregator and you have a series of events that you fire into that aggregator, and then you apply an additional event. You say, okay, well, given that this event just happened under this new state, right?
It's commands, but yes.
Oh, sorry.
Yeah, commands mutate the state. Events are the result of that mutation.
When you update a command, do you find that like going through all the tests and updating those tests is like present?
Yeah, it can be. You try, so one of the principles of domain-driven design is you try to identify these things up front, and you really try to capture as much as possible. So that's definitely a challenge, is when your commands or your events change shape. And typically, you just create a whole new command. So in production, a lot of times what we do is we version our commands and events, so that instead of modifying an existing one, we're just creating a new one. And then we can maintain that existing command handler and just layer the new one on top of that, and then eventually we can deprecate the old one.
I wanted to ask about, I don't know if you have this use case, but like single time side effects and whether you have any issues with replayability and having to guarantee that side effects will happen more than once.
Oh, sure. So like you go out to like Stripe.js and like request a payment. You obviously don't want to like do that multiple times. Yeah. So that's a great point. Usually, what you do is per your event handler, you could say, I want to do this during replays, or I don't. So you could have an event handler that generates your projection, which updates the state of your relational database. You might have another one that actually goes out to Stripe to request payment, and you would just say in that one like, do not do this during replays. But the nice thing is, in your event store, if you received the response from Stripe and you log that as an event in your system, you don't need to go back out because you have that data and that response. So you can still rebuild the state based off the response that you got previously.
event sourcing work in the context of customer privacy where we need to handle deletes, for example, in the case of GDPR?
Yes, great question. Really good question. And this is actually something that, on the face of it, isn't really compatible with our immutable, append-only data store. What people typically do is they actually do have tools to modify the data store in very careful ways. So, for example, in our model, we're tracking the user who submitted the order, right? So, in theory, we could go back to let's in Europe, the customer could request to be forgotten. So you could go back and just expunge the event store of all of the orders that customer has submitted. It can be a problem, and it's definitely a good call out. And I don't know if anyone's really come up with a great solution. I think everything that I've read is just be careful. Like, you need to do it. You need to modify your event store, but do it in a very careful and controlled way. So I know that's not much of an answer, but that's the prevalent wisdom.
Anyone else?
Okay, great.
Thank you very much.
Thank you.